and handled by myself, Esakishan, and Harshul Jinri. And I welcome everyone to the greatest event and good evening to one and all present here. I am Esakishan, representing CheckDate, and I take immense pleasure to welcome you all to the first ever international research custodian and extravagant event with illustrating panel discussions, enlightenment, and knowledgeable speakers from various respected speakers from across the world, and of course, an ocean of uh, an ocean of opportunities for you in form of networking sessions, ideological competitions, and research expo. Now I hand over this to Harshul.
Check did a student-based research initiative created with a vision that many believe cannot be a possibility. We strive to deal with real-world problems and find solutions that have never been created and improvised using the help of technology, human expertise, and a touch of empathy. CheckDit delivers you the solutions, innovations, and hope for a better tomorrow. CheckDit, along with its collaborators, Affinity, Heartfulness Organization, BMSCE, eCell, IIT Mandi, IEEE, BMSCE, ACM, LNMIIT, Code Chef, VIT Chennai, Microsoft Innovations, Club VIT Chennai, Music Club VIT Chennai, Dance Club VIT Chennai, Skillanta, Ojasvi LPU, and Dramatics Club VIT Chennai, and his sponsorship with Varivo Motors and EduCheck brings you an extraordinary platform where discussions ranging from AI to mythologies will be incorporated among the youth and raise competent minds for the betterment of a future of a nation. Now
Now,
into the discussion.
thank you, Harshul. Now, without any further delay, let us get to the moment. I'm sure everybody is waiting for it. I would like to give the floor to our respected speaker, Dr. Abhijit Adiga. Sir Dr. Abhijit Adiga, a research assistant professor at University of Bergen, US. He did his Bachelor of Engineering from University of Bangalore. Thereafter, did pursued his PhD from Indian Institute of Science, Bangalore, in computer science. He was once also a senior of research assistant from year 2016 to 2018, and thereafter research assistant professor for year 2016 to 2018 at Virgin Tech. Dr. Adiga is a diversely skilled person with specifications in computer science, data analysis, algorithm, simulation, and commutable modeling. He is an incredible person with so much experience and knowledge, and his positivity is ineffectuous. Now, the stage is all yours, sir. Please hand over it.
Thank you, Kishan, for the great introduction. I Good afternoon, everyone. First of all, I would like to thank all the organizers for organizing this so well, and in particular, Dr. Rajeshwari Hegde, Madam, for giving me this opportunity. And also a very insightful and interesting talk by Dr. Athri. I hope I can do justice in this talk. Okay, so the title of the talk is How to Stop an Epidemic, a fancy title given the current scenario. But I've been doing this kind of work for the last 10 years, and I'm going to share my experience with you. So, since most of you wouldn't know me and my work, I thought I'll share my academic background, and also it helps in you to know how I approach my research. So that's the idea, and then I'll move on to the technical part of the talk, which the first part would be modeling complex phenomena like infectious diseases. And then comes the main part, the how to stop an epidemic. And I'll talk about further about how to create simulators, and that's where we look at digital twins. Okay, so my background, as Kishan mentioned, it's in telecommunication engineering. I did from BMS, College of Engineering. And my master's was in signal processing and communication, where I learned about discrete cosine transforms, image compression, and so on. And on the side, I also did a lot of information theory, error control coding. Then I had a great 2 years industry experience in BCM communications, where I did a lot of WiMAX technology, where my main job was to develop algorithms for the physical layer algorithms, physical layer in the communication pipeline. So this was my world. And in around 2006 or so, everything changed because I moved to computer science. It was a very abrupt decision, where I started working on discrete mathematics. And my PhD was in geometric intersection graphs. And mostly what I did was graph theory, geometry, combinatorics, and so on. So it was lots of theorems and proofs, and so on. So why talk about all this? So then when I went for my postdoc and came here to the Biocomplexity Institute, which was then called the Virginia Bioinformatics Institute, um, I was able to put all these things together and make use of it to what we do here. So what do we do here? So we are basically uh, um, a team of multidisciplinary individuals, researchers, working on network science and simulation systems, and I'll explain more about our work. Um, so what is it? So we basically develop science and engineering of massive networked interacting systems, and I'll give you examples of these as I move on in my talk. So one question that we answer is, or address, is how can one detect, respond, and reduce the impact of a pandemic outbreak? So earlier I had to motivate this a lot, but now I don't have to. Most of us, all of us know what we are going through, and we have had first-hand experience of it. Then another example would be, how can one prepare for, say, a human-initiated nuclear detonation? So this again is an unprecedented but extremely high impact event, and these are questions that every country asks and prepares for, either secretly or not. So why can't these problems be solved using traditional approaches? So what do I mean by a traditional approach? It's like a one professor with students working. So it's not possible. Why? Because as we have seen in COVID case, um, there's so many things to come together. You have the economics of it, you have the biology of it, the social interactions of it. So you need people from various disciplines to come together, and this is exactly what we do. And this is just my funding and collaboration. Our team does a lot more. So these, I would like to acknowledge the various agencies that have funded my research, and I have had the pleasure of working with people from various countries and various domains in the last 10 years. Okay, so what is my research about? So basically, it has three aspects, as you can see here. So one part is modeling complex phenomena. The other part is more of a theory side, or the mathematics side, where I do theoretical computer science, network science, and so on. And then there is the data part of it. So now everybody is a data analyst now. So I too had to don that hat, and with pleasure have donned that hat. Um, and the amazing thing is, all my academic background that I described briefly in my previous slides, all of that has come together uh, to help in my research, whatever I do right now. And on the side, what you see here are all the applications that I have worked on in the last 10 years. So what are these three aspects that I have mentioned here? So first, modeling complex phenomena. What does it really mean? Um, so basically, modeling means representing real world phenomenon as a mathematical or a procedural object. So when I say mathematical, it could mean equations. So procedural means you can even represent it with a code, like a video game, for example. Then, so what is a theoretical aspect? So basically, you take this mathematical object, the model, you analyze these models and design algorithms for solving real world problems, which have been expressed mathematically using this model. And what do I mean by data science? It can mean different things for different people. For me, it's basically creating digital twins. That's what our team is well known for. So we basically construct realistic simulation systems of these complex phenomena that we study. Basically, it is data plus model plus engineering, and all this will culminate into this object which you can use, the simulation system that you can use to study the real world phenomena. So in each of these, what are the methods that I use? So for modeling complex phenomena, you basically cannot do it on your own, because I am a computer scientist, and um, I can work with the mathematics part of it, but I don't know anything about how COVID spreads. I don't know anything about how an invasive species spreads or how transportation happens. So for that, for each of these, there are domain experts who have been studying this for 50, 100 years. So we have to collaborate with domain experts, people on the ground, and we do things like instituting surveys and so on to collect more and more relevant data. Then, then the theory part. So here I have been using uh, from my academic experience graph theory, algorithm design, game theory, and computational complexity. And for so far as the data science part is concerned, of course, I'm using machine learning. Then there's a lot of data exploration that happens, statistical analysis, and HPC and so on. Okay, so this brings to my second part of the talk, where I'll focus on the first aspect that I talked about, that's modeling complex phenomena. So as I said, modeling is a mathematical or procedural representation of the phenomenon being studied. And we have been doing this since our probably middle school. Like for example, we start with Newton's laws. These are not uh, perfect, and we are not aware of that until after some time. They have these assumptions break at some point, but they are useful, right? So that's why there is this by now cliched quote saying all models are wrong, but some are useful, and some are really, really useful. And we have similar, over the years, you would have seen weather models, and now we have disease spread models, which have become much more sophisticated than they were 20 years back. And I'll be giving a glimpse of these models in this talk, the disease spread models. Then, so why do we need these models? Why can't we simply think and study about these real world phenomena? So basically, a model helps study the phenomenon in a principled way, and helps make use of tools developed in mathematics, computer science, statistics, and different domains, like even economics and psychology. And the other important thing is generalizability. So what a modeler would like to do is use the same class of models for different applications, and I'll show a glimpse of this as well. So that's why I say, so one ring to rule them all in the Lord of the Rings manner. And basically what I'm trying to say is, we would like to so when we do this, when we have many applications, many phenomena being represented by one type of model, the advantage is you can focus now on that model, and once you solve something for that model, you're able to apply it to all these applications. So that's the beauty of it. So now comes the network dynamical systems that I have in my title. And where have they been used? So, and this is just a subset of the examples that I'm showing here. So of course, they have been used in public health. The infectious diseases can be very effectively represented using as a process over networks. So for example, you have COVID, and then you have at the same time you have the ALS ice bucket challenge, which many of you might remember, though it's a long distance past now. So one is, both of them are social phenomena, but one has a more biological aspect to it, the other is has an even more behavioral aspect to it. Nevertheless, both of them can be represented as spread of something over a network. And what is this network of? This network is all about people. So each node in the network is an individual from a population, human population. And what is the edge? So two nodes or two people are connected by an edge if there is either a physical contact between them, in this case as in COVID, or there is a social contact between them. So social contact necessarily doesn't have to be physical contact. It could be a friend over Facebook or so on. So this is how you can use network models to represent these phenomena. And it is not limited to just these applications. You have cyber security, where a malware spreads over uh, a network of computers. Then there is infrastructure, like component failures in smart grids that we have seen recently happen. And then there's also financial crisis among institutions, where each node is a financial institution. So basically what is common to all of these is massively interacting networked systems. So how do we model such phenomena? I have a very simple model here, which surprisingly can be uh, which can be applied to several phenomena, including infectious diseases. So basically, we have a network. Then we have these nodes, which can represent many things depending on the phenomena. And these nodes are associated with states. In this talk, I'll consider just state 0 and state 1. So 0 means you don't have the disease, which could be COVID. 1 means infected, you have the disease. The nodes change state as a function. So there is some function that decides what your state is at any given time. And that function depends on your state as well as your neighbor state. It's that simple. So for example, take this node here, the leftmost node here. Its neighbors are just this and this is not a neighbor. So what I'm saying is, at any given point of time, the state of this node depends only on these four nodes, which means it includes this one. So what we are interested in is, okay, I'm given this local behavior of a person. When I say local behavior, it is fully captured by this function. So what happens given this local behavior? What will be the global behavior? That is what is the system behavior? So one concrete example is, given the way people are interacting in a population, say without wearing a mask, then what is going to be the total number of infections? So that's what I'm interested in. That's only one thing, but the total number of infections is the global behavior, whereas the fact that I'm either not wearing a mask or not wearing a mask is a local behavior, because it's more of an individual decision. And here is a particular example, which is actually pertinent to infectious diseases. So we have three states, so not two, but three states here for an individual that is susceptible, infectious, and recovered. So how does this work? So each edge has a probability, and if this person is infected, this person will infect this person with probability 1, and this person with probability half, and so on. So every time step this happens until this person recovers, and after that he'll not be infecting anybody. So once she is infected, or say she is infected, she will try to infect uh, her neighbors, and this way the population, the infection spreads over the network. I hope I've made this clear. Otherwise, feel free to post your questions on chat. So how and implementing this is very simple. Depending on your coding expertise, you can do this in anywhere between half an hour to a day. You'll be able to achieve this simulation. And how do you do this? You implement the rules of the state transition for each node. You also construct the network, and based on the context, identify the seed nodes. So seed nodes means this patient zero, like the first person who got infected, and these seed nodes are infected at time zero, and then the infection spreads in each instance. So you run multiple instances of this. Why? Because this is a stochastic process. Every time, so there's a lot of probability involved. So every time you get a different outcome. So what we are interested in is, on an average, how many times was a node infected? So that would be like, how vulnerable am I in a population to get COVID? So that if you want to ask that question, then it comes down to vulnerability, and that's precisely the question that we can ask. And as I said, in stochastic settings, average values are important. And I guess I have made some text vanish here. Sorry about that. But in reality, real world phenomena, the models are much more complex. So what you are seeing, what I showed you before was so simple, and hopefully you understood it. But what you have in reality, the COVID, for example, this is the model for COVID that the Center for Disease Control in the US proposed. And there are many models floating around, but they're all very similar. And you can see it has so many states. This is not the network of people, by the way. This is for one individual, what are the possible state transitions when the disease happens. So you are susceptible, and when you are exposed to the disease, like you come in contact with somebody and you get the virus, then what happens, what all could happen. So this is what is captured by the state diagram here. And similarly, I have worked on invasive species spread. It's the same kind of phenomenon, but you can see that the model is quite different here. Okay, so I basically work in artificial intelligence. So I always get this question: can't all this be solved by deep learning? So nowadays, machine learning, deep learning have taken over, right? Mm, and rightly so. They have had a tremendous impact. The accuracies and the effectiveness has increased probably tenfold, hundredfold, and there are so many stories to validate that. But the thing is, this hammer is not for all problems, or I should say, this is not the only tool you can use in every and get away with in every situation. So first thing, it is not always about data. So in the case like COVID, in fact, you don't have data available, right? Especially in the beginning. But then procedural knowledge is always available, like how people behave, how do viruses infect people, and how do people infect each other with this virus. So this has always been studied. For example, influenza has been studied, malaria has been studied. Slightly different from influenza, but still the behavioral process is still there. So and also, as I said, in many real world scenarios, data is simply not available. So once you don't have that much data, like you need thousands, ten thousands, a million, millions of data points, if you don't have that, it's hard to do deep learning. And also, it is not just about forecasting. So what do these machine learning algorithms do? You basically learn from data, and then the next time you get an unlabeled data, that you basically say, okay, where should I put this? And or you say, till now, whatever I know about the disease, in the next time instant, how many people will be infected? So this is the forecasting problem. For these, actually, the deep learning methods have been used, and they're pretty effective. But it's not just about forecasting. It's also about understanding spread dynamics, like prediction of routes of invasion, causality, what is the reason why this is happening. So these things are not effectively answered by machine learning alone. Okay. And there are many other things like guided data collection, informing prevention and mitigation efforts, and so on. So there's an excellent article by Joshua M. Epstein on why model. I would encourage everyone here to take a look at this. It's very nicely written. Okay, this ends the second part of my talk. So the third part, it's it's all about the theory, and you don't have to run away. I will not be bombarding you with equations. There might be a couple of equations here and there. I understand that you come from diverse backgrounds. Um, so here, the application is pushed to the background. Like I mentioned, if you remember, one model to rule all, right? So basically now the model comes to the focus. It's all the mathematics that comes to the focus, and we don't care about the application as of now. Once we have a solution using the model, then we can translate it back to the application. So this is a very different research hat, and I'm fortunate that I have the academic training in this. Um, so to just give you an example of what a computational problem looks like in the context of epidemiology, take the example of an inverse problem here. So inverse problem means I would like to know the source of the infection. So when say COVID started, which area in China did it start from? Like you want to get into the very specifics, not just a district or somewhere, but which building or so on. So that is a very important question, right? So that's also called the patient zero. And then there are other things like estimating the transmission probability and so on. And when it comes to patient zero, for example, in the network, it corresponds to what is known as the index node or the source node. What is my source node for this infection? So basically, you forget about the disease spread, rather you make it into a network problem. Okay, so that's what a computational problem means in at least in this talk. Right. So there are so many ways in which you can intervene, right? So there are vaccines, and then there is social distancing. So you'd be surprised. 2 years back, I had to have 2-3 slides on social distancing because nobody would believe that these things are required. And then there's also site closures using protective gear, etc. And how do we model these interventions in the network system? So you can see that all these things can be modeled this way. So closing work is same as cutting off edges between two locations and people, or well, it really depends on how you model it. In this case, it's people to people network. You're cutting off this edge and this edge because these two people are co-workers. All these people are co-workers. So once you cut off these edges, once you close the workplace, you're automatically cutting off these edges between these co-workers. And similarly, you can do isolation, quarantine, etc. And so depending on the intervention, it can be a node intervention, edge intervention. See, node intervention is like vaccination. So when you vaccinate a person, let's say the vaccination is 100% efficient, then it means it's a node intervention. This node or individual is no longer part of the disease spread phenomenon, right? So and also all of these interventions are budgeted problems. As you can see, there is a cost to intervention. Closing schools, it has a cost. Vaccination has a cost. So these so therefore, and also there is a limited availability, so you don't have infinite number of vaccines available. So that's what makes it a budgeted problem. I have only 10,000 vaccines. Who should I distribute it to? So these are the questions. And there's also the efficiency, which I talked about. And here comes a fundamental question: why theory? So why can't you simply run your code and try out these things and report it? Because people have been doing this. They use their favorite programming language, anyway, C++, Python, even Excel sheets, they use them and then come up with these their methods. How effective is mask wearing, how effective is vaccination, and so on. But is that enough? So basic question is, how do we convince ourselves and others that our strategies are good? By simply running 100 simulations? What if you had run 10,000 simulations, and what if the outcome was very different? So it's very important to come up with optimal and near optimal algorithms. And this is where theory helps. So theory gives you certain guarantees. So if this is the best strategy, whatever strategy you have come up with is, say, 1.5 times the best strategy or some such thing. So this kind of quantification of the quality of your algorithm, you can only do it with theoretical constructs. And how do we know that we can actually come up with a good strategy? So that's where computational complexity comes in. So if there are computer scientists in this room, you would have definitely heard about NP hardness and so on. So this is a big part. So if you have to say that, okay, vaccination is a very hard problem, how do we justify this? One way to justify it, just one way, is computational complexity. It doesn't mean that you cannot come up with effective strategies, but it does mean that it's a hard one. This problem is a hard one. And also identifying limitations of model and data. So I collect some data and make a model, and I use the model, but how true is this model to the actual phenomenon? So this you can quantify. For this you have validation, uncertainty quantification, and so on. And these are only very few things that I'm talking about. There are many more things that theory has a role to play in. And of course explaining the behavior of the model. And the very basic thing is, once you see, there's so many mathematicians, statisticians, machine learning people who have worked for 100 years now, leverage, and we would like to leverage this work, right? We don't want to simply invent this wheel over and over again. So that's one reason why you would like to use the past theoretical framework for the present day problems. Okay, with this, what I will do is I'll quickly tell you about the different types of vaccination problems that are there and that I have worked on. I might have omitted some of them, so I apologize for that. So the simplest problem is the centralized vaccination problem, or the targeted and centralized vaccination problem. So here, let's say it's a country with an autocratic rule, and the government says, okay, and again the context is this: you have limited number of vaccines, so everybody can't be vaccinated. So given that, the job of the government is to pinpoint the individuals who should get vaccinated. Okay, if that is the problem, then that can be translated to the network as follows. You're given a network G and a budget B. Budget is the number of vaccines. So find a set of B nodes to vaccinate so that you can minimize the expected number of infections. So what is the expected number of infections here? So you vaccinate people, and then you run the simulation multiple times, because as I told you before, it's a stochastic process, a probabilistic process. Every time you run the simulation, the outcome could be different, right? So on an average, we want to reduce the number of infections, and we want to minimize this. We want a solution that minimizes this. So this is the targeted or centralized vaccination problem. Okay. And now there are many other flavors, and while the targeted problem, very simple to state, it is kind of contrived, right? It is very simplistic as well, and not really it's not a realistic thing. Like, it's not a real world problem. It's a bit far away from the real world problem. So we'll approach the real world vaccination problem, and there are a number of aspects that I will talk about now. So first thing is the decentralized vaccination. So here, nobody forces you to vaccinate, but you're incentivized to vaccinate. So you are given, there is a cost of taking the vaccine. So in the COVID case, you're given for free, but there is the taxpayers' money going in there. But let's say there is a cost of taking the vaccine, and there's the utility. It really depends on other strategies. You can decide not to have the vaccine, but if you don't have the vaccine, then there is this coin toss, right? So you can, if you don't get the disease, then you haven't had the vaccine, so you don't have the problems of, say, missing work, or paying for the vaccine or some such thing. But at the same time, if you get the disease, then you have a huge cost. So you can formulate, you can take all this into account and formulate it as a game theoretic problem. And I won't go into these details, but when it comes to game theory, what we study are equilibriums. So one popular equilibrium is the Nash equilibrium. So one question that comes up is, okay, if this is the cost and this is the utility, then how many people in the end will be infected? How many people will go for the vaccination? And this is all people's decision. This has nothing to do with the government or anything. The government's job is to control people's behavior by just by just manipulating this cost and utility. So then there's also group vaccination. Say the central government decides that this much vaccine goes to this state, this much vaccine goes to this state, and based on some strategy, and that is the strategy that we have to come up with. But once this is distributed to these individual states, the central government doesn't have any control over how the state government distributes it within the state. So this is the partial control problem, and there is also a region-wide intervention problem, which I won't go into because of time constraints. But I'll be happy to talk to you about it offline. There's also the multi-stage vaccination, and we have gone through it. This is not the case where you have the first vaccine and then the second vaccine, then the booster, and so on. This is the case where, okay, few vaccines are available, who should I give this to? And after 2 months, more vaccines become available, then who should I give this to? So this is the kind of problem that we have worked on. And these are extremely hard problems. Even the simplest centralized vaccination problem is hard, computationally hard, but many people have come up with very effective solutions. But this multi-stage vaccination and the other one, the group vaccination, these are extremely hard problems. Okay, so I'll give a glimpse of my work in this, and this was done like 5 or 6 years back before we knew about COVID. Okay, and this is for the centralized vaccination. So we would in high school or pre-university or wherever you would have learned about eigenvalues, right? The basic mathematics, advanced mathematics, but you would have learned this somewhere in your at some point in your school. So we use this concept. It's a very simple thing. You can assume certain things here. So you are given a graph 1, 2, 3, 4, and then you construct an adjacency matrix. So what is an adjacency matrix? If node 1 and node 2 are adjacent, so here, which they are here, you have a 1 here. If they are not adjacent, then you have a 0. Okay, so this way you construct a square matrix called adjacency matrix. Now the spectral radius is nothing but the largest eigenvalue of the adjacency matrix. So why is this largest eigenvalue important? So first of all, this is how you can compute, very easy to compute this. Some matrix operations, you can compute it, and you'll know what the eigenvalue is. So why is this important? So there is some great work in epidemiology where they show that this is linked to disease spread. Okay, how is it linked? So take the disease. So this is purely a disease parameter. T is a threshold. So basically the recovery rate divided by the infection rate of the disease. You can think of rate as probability. It is not always called always probability, but you can think about it that way. The infection rate is how quickly does one person infect another, recovery rate is given that I'm infected, how quickly can I recover from the disease. So given these two, um, you get this threshold. So if the first eigenvalue or the spectral radius is less than the threshold, then the diffusion dies out. If it is greater than the threshold, then the diffusion becomes an epidemic. That is, what I mean is, small amount of spread will lead to a large population getting the disease. Okay, that's what I mean by it becoming an epidemic. And there are many models for this which this has been shown. So what we did is, we didn't worry about the simulations and or anything. So we just took this simple problem. My job is to remove the nodes of the network or edges of the network so that I bring down this eigenvalue, this first eigenvalue. So if I do that, and if I bring it down this threshold, then I have achieved my objective, right, of controlling the spread. So that's exactly what we set about to do. And so basically, why do we do this? So from a diffusion problem, so we have this network diffusion process. From that problem, it becomes a purely network structure problem. So you're now focusing only on the network. You don't care about the process. So we came up with some what are known as approximation algorithms. I will not go over that, but basically, approximation algorithm means if um, removing, so if you have k nodes that need to be removed, then we came up with, say, a solution with 2k nodes, okay, which does a good job. So and we have these things which I will not go over. So we have 2 3 algorithms that we came up with, which give very good performance and are very fast as well. And the coming back to a very recent work, just a few months back, we did this work in the context of COVID. It was a huge group effort, contact tracing and social distancing. So this is also an intervention, right? So you target people who are infected and their neighbors, and then force them to quarantine. So this is what contact tracing and social distancing combined is. So these cannot be captured by just the structural network measures. For this, you need to run simulations. Why? Because only after a person is infected, you can intervene, right? So we came up with certain methods based on full knowledge and partial knowledge. So a government doesn't know all the people who are infected. So we also considered that scenario where you know only 10% of the people who are infected. So what we observed is, when you do contact tracing, there is minimal change in network structure. So when you make these people quarantine and so on, but it leads to a very effective mitigation of disease spread. So that was our the outcome of our research, and I'll be happy to explain these plots offline. Okay, so till now I was focusing on the model, on the theory part, but I never talked about the actual simulator and how we actually construct these simulators. So that's where the data part enters. So this is the third aspect of the kind of research I do. And I have probably 5 minutes and I'll try to be quick about this. So we come to the concept of digital twins, which is taking shape nowadays, becoming very important, especially after COVID. Um, so what's a digital twin? So digital twin is basically a virtual representation that serves as the real-time digital counterpart of a physical object or process. So it's like a video game of a real world phenomenon, right? Mm, so here, what we are really interested in, realistic but virtual representations of socio-technical systems. So what do I mean by socio-technical systems? The spread of COVID is an example of a socio-technical system, but there are many more. And these happen at different spatial scales. So we can study them at the level of university. How is COVID spreading once you reopen a university and people start pouring in? How does the spread happen? We could look at it at a city level. You could look at it at something else. Like, you can forget about infectious diseases, but food systems contamination, or power, transport, communication, and so on. And these are, we have to understand, these are very crude approximations. So however sophisticated your simulation system is, it's a very crude approximation of the real world counterparts, because it's physically impossible to represent the real world phenomenon because of anonymity and sheer data you need. So if you, for every individual, you will need the data that is required, and you lose anonymity, privacy, and so on. So that it will never happen, at least in the near future. And even if you can gather all the data, how will you process it? I think terabyte would be bytes of data would you'll get from just one individual. And also it is dynamic or ever changing, right? So this is another thing to cope with. Nevertheless, these are useful. Digital twins are very useful. So I'll quickly go through two applications. Probably the first application that focuses more on COVID, and if time permits, I'll go over this one, the agricultural commodity flow. So this is something our group has been doing for the last 15 years, synthetic populations of humans. And we have applied it to so many phenomena. So what is a synthetic population construction? Basically, we construct this network for the simulator, but how do you construct it? So you take a variety of data sources, like population information, census, then surveys, and you also look at how people behave. So because once you get the population information and from the census, what you get are the nodes of the population, but still you need the edges, and these edges also change with time. So all these things, how do you get from so what kind of data do you use to construct this? So that is what I'm going to explain now. And this is made possible only because of high performance computing. So we have thousands of compute nodes that we use. We have a cluster that is constantly running to generate these networks. So as I said, there are multiple data sources, the census, then there are activity surveys. So people, what do they do on a weekday or on a weekend? So these kinds of activity surveys are there. So based on that, you can construct the edges between two people. And there's the building database. So you would like to know whether this node and this node, they belong to the same household, or do they work in the same place? So for that, we use the building database, and these are all approximations. These are not exact representations. So these individuals, they are just in quantity, they represent the entire population, but they don't represent any particular individual from that country or city that you are studying. Then there is points of interest and so on, because you need for that activities, etc. Okay. So the basic thing you have to get from this is a very non-trivial process with probably around 10 to 50 data sources, and these data sources vary from one country to another. So every time you have to restart this operation. So for the University of Virginia, recently we did a analysis on how COVID would spread if students came in, and this is part of the work that I'm presenting. So we basically created a UVA digital twin, and the components were the students and instructors are the people. Then you have these dorm locations, hostel locations, lecture halls, etc. And also you have complete trajectories. So we instituted surveys, and we came to know how people move from one building to another on a weekday, on a weekend, and so on. And we took all this and we constructed a network, and you can see here for every building in the in UVA, based on office cubes and office spaces, we came up with edges between people and so on. So this is this is the construction of synthetic population. We have done a similar thing for invasive species. I'll just give you the motivation and end this talk. So basically, last 5 years I have been working on this pest called tuta absoluta. By the way, this is in India and it's a big problem. It came from South America to Europe and from Europe to India. It affects the tomato plant, and the amazing thing is it's a very tiny insect. And but despite all this, it has spread around 800 kilometers every year. And how did it do that? It just spreads on our trade networks, the tomato trade network. Okay, it just pupates in boxes, small boxes, and once it goes to the destination, it becomes a moth and it spreads. So we were asked to model the spread, and you can see here my Indian collaborator has taken pictures of this. And there are many ways in which it can spread, not just by flying, but by trade, by travel of people, and so on. And we came up with a model for this. Um, and as you can see here, there are so many data sets that we have used to construct the simulator. And I will of course not get into the details of all this. And these are some networks for this food systems that we have constructed to address this problem. These are time varying networks. So you can see that in the month of January, this is the network of flows of tomato from one place to another, whereas in the month of September, it's increased, and this is a totally different scenario. So, okay, so I would like to end this talk and not take up more time. So, the key takeaways are basically there is a holistic approach that's required to understand and control complex natural and socio-technical phenomena. It's not just understanding, right? Also need to control it, like in the case of COVID. So, what does that mean? That means that you need multiple data sources to come together, multiple domain expertise to come together. So, for example, my team consists of several computer scientists, but it also consists of economists, psychologists, epidemiologists, and so on. Then we have multiple techniques that need to come together, and I described them. Um, so advances in big data analytics and high performance computing have made it possible to realize this, and is only going to improve. So you're going to get more and more high resolution digital twins. And to be specific about the kind of work I do, so network dynamical systems, which I described today, the basis of this talk, this approach can be used to study a wide variety of phenomena. And why? Because many phenomena naturally yield to this network representation, as we saw today. There's a rich body of theoretical tools, and a variety of network-based data analytics are also available. Okay, with this, I would like to end the talk. And again, thank you very much for this opportunity.
Thank you, sir, for the enriching and intense session. We have surely been enlightened, and sure the audience is going to take home a lot of knowledge and knowledges today. If anyone from the audience has any queries, please let our esteemed speaker know. You may unmute yourself or drop your queries in the chat.
Okay, guys, as nobody has asked any queries, we have one more a best part of this is that we are conducting a merge internship program where after competition, certificates and a letter of recommendation will be provided to the interns who have performed extremely well. For more information on this, please check the website check our website. Also note, participant certificates will be provided only to them who have attended this session, our session for 10 hours during the consortium. So kindly fill the feedback form for the same at the end of the session. Now I hand over it to Herschel.
Now it's time for a vote of thanks. For that, I would like to invite Anushka.
Yeah, good evening. Firstly, I would like to thank our speaker, Dr. Abhijit Adiga, for taking out time and agreeing to be our speaker for this consortium and delivering such a great session. I am sure everyone took back a lot from this session. Nextly, I would like to thank our mentor, Dr. Rajeshwari Hegde and Dr. Susan Elias for guiding us throughout so that our team could execute this. Last but not the least, I would like to thank our outstanding audience. Dear audience, stay tuned for an exciting session on living with holistic approach by Dr. Mohandas Hegde. Thank you, sir. I would like the team to present the certificate of appreciation.
Thank you very much.
Thank you very much, Dr. Adiga, for your kind contribution and for accepting our invitation for being our speaker for this consortium. Please accept the moment of gratitude from our end, sir. We are extremely thankful for having someone like you for the session. Thank you very much for enlightening us.
Great. Thank you so much for this opportunity and for this honor.
Thank you very much, sir.